Something happened on January 18th, 2026 that the sun has been building toward for months. At 1:09 p.m. Eastern Time, observatories around the world detected a coronal mass ejection, an explosive burst of superheated plasma and magnetism from the solar surface, and the CME struck Earth's magnetic field the following day, landing the most powerful energetic punch since the Great Halloween Storm of 2003. The Northern Lights appeared over Canada, much of the United States and Europe. Power grid operators scrambled, airlines rerouted flights, and the sun, which has been doing this repeatedly for the past year, simply kept going, producing 5 massive flares in a single week in early February alone, including an X-8.1 that released energy equivalent to 1 billion atomic bombs. The question is not whether this is unusual, it is. The question is, what exactly is happening, what the physics says about it, and why the gap between what scientists know and what the public understands about these events is as wide as it has ever been. The sun is not a stable star in any meaningful engineering sense. It is a plasma object the size of 1.3 million Earths, held together by gravity while simultaneously trying to blow itself apart through nuclear fusion at its core, churning at differential rotation speeds across its latitude bands, threaded through with magnetic field lines that twist and tangle and snap and reconnect with the force of something that has no good analogy in human experience. When a solar flare erupts, the explosion can release as much energy as 1 billion atomic bombs, and a torrent of electromagnetic waves leaves the sun at the speed of light, arriving at Earth 8 minutes later, potentially disrupting shortwave radio transmissions and causing errors in navigation systems. 8 minutes. The light from that explosion reaches your retina at the same moment it reaches every satellite in Earth orbit and every radio antenna on the planet's sunlit face. There is no warning system fast enough to intercept it. The warning comes after. The warning is the disruption itself. ESA. What makes the current solar cycle different from most people's mental model of the sun is scale and timing. Since one sunspot region emerged on January 30th, 2026, it produced 21 C-class, 38 M-class, and 5 X-class flares, including the X-8.1. And forecasters noted that the massive sunspot group remained magnetically complex, with solar flares continuing to be likely. 38 medium-class flares, 5 extreme-class flares. From one sunspot region, in days. This is not background noise. This is a star in a specific phase of its 11-year magnetic activity cycle, and that cycle has been running hotter than predicted. Solar Cycle 25, which began around December 2019, was forecast by a panel of experts to be modest, similar to the weak Cycle 24. Instead, it became one of the most active cycles in recorded history, consistently exceeding predictions by significant margins and showing no signs of peaking at the level that had been modeled. The Boston Globe. The physics of why the sun produces these events is understood in broad terms and deeply contested in the details. The sun's magnetic field is generated by the dynamo effect, the movement of electrically conducting plasma through existing magnetic fields, which generates new magnetic fields, which drives more plasma motion, which generates more field in a self-reinforcing cycle. This dynamo operates across the entire solar interior and produces the 11-year cycle through mechanisms that solar physicists can describe mathematically, but cannot yet fully predict. Sunspots are regions where intense magnetic flux tubes break through the surface, locally suppressing convection and creating areas that are several thousand degrees cooler than the surrounding photosphere, which is why they appear dark against the brilliant solar disk, though each individual sunspot contains enough energy to power human civilization for geological timescales. When these magnetic field lines, stretched and stressed by differential rotation and convective turbulence, undergo reconnection, meaning when opposing field lines snap together and reannihilate, the released energy accelerates charged particles to relativistic speeds and sends them outward as a coronal mass ejection. Following the electromagnetic burst, a fraction of an hour behind, come high-speed solar particles including protons, electrons, and alpha particles. This radiation can harm astronauts, damage spacecraft, and can produce a cascade of secondary particles in the atmosphere that could cause errors in electronic components if they reach the ground. The January 2026 event demonstrated this directly. The high-energy particle shower peaked in intensity at 1915 UTC on January 19, 2026, reaching severe levels, S4, placing it at the top of the list of the most intense radiation storms in the GOES satellite records. S4. The scale goes to S5. We were one level below the highest radiation storm ever defined by the modern measurement system. Astronauts aboard the International Space Station sheltered in the most shielded sections of the station. Polar route flights were redirected at significant cost. On Veterans Day 2025, a preceding severe geomagnetic storm produced a powerful X5.1 solar flare that caused more than 30 polar flights to be canceled and forced Blue Origin to scrub a rocket launch for 24 hours due to elevated radiation exposure risk. ESA +2. The geomagnetic storm component, the G-scale events, represents a different mechanism and a different set of risks. When a CME arrives at Earth, its magnetic field interacts with Earth's magnetosphere. If the CME's magnetic field is oriented southward, anti-parallel to Earth's northward pointing field, it drives magnetic reconnection on the day side of the magnetosphere, energizing the Van Allen radiation belts, driving intense currents in the ionosphere, and inducing voltage spikes in any long conductor on the ground. Power transmission lines, oil pipelines, railroad tracks, undersea cables. The longer the conductor, the larger the induced voltage. During the strongest historical geomagnetic storms, the Carrington event of 1859, the Quebec blackout of 1989, the Halloween storms of 2003, telegraph systems caught fire, transformers exploded, and 6 million people lost power for 9 hours in the middle of a Canadian winter. The CME from the January 2026 event struck at 2:38 p.m. Eastern Standard Time on January 19th and triggered severe G4 geomagnetic storm conditions far earlier than initially forecast, with space weather forecasters confirming G4 storm levels were reached shortly after impact. G4, one level below the maximum, again. Space.com. What space weather scientists find troubling about the current cycle is not any single event. It is the frequency and the trajectory. Solar maximum, the peak of the 11-year cycle, was expected somewhere around late 2025 or early 2026. Based on the number and intensity of flares and CMEs, the cycle peaked higher than any consensus forecast had placed it. And while activity typically declines after solar maximum, the descent is gradual, and the largest individual events in a cycle sometimes occur after the peak, not before. In May 2026, a colossal solar flare erupted on May 10th, unleashing an M5.7 coronal mass ejection and triggering radio blackouts on the sunlit portion of Earth, with space weather forecasters warning that even a glancing blow from the associated CME could trigger minor geomagnetic storm conditions. The Sun does not know it is supposed to be winding down. Daily Galaxy. The infrastructure vulnerability question is one that emergency managers and grid operators have been studying for years, and that the public largely ignores until something breaks. The modern power grid was not designed with geomagnetic storms in mind. Long-distance high-voltage transmission lines, which backbone electricity delivery across continents, are particularly susceptible to geomagnetically induced currents, GICs, because they act as enormous antennas for the slowly varying magnetic fields produced during a major storm. The transformers at the ends of these lines were not designed for DC offset currents of the magnitude that a Carrington-level event would produce. The thermal capacity of a large power transformer takes months to manufacture, costs tens of millions of dollars, and cannot be easily replaced if damaged. A simultaneous failure of multiple high-voltage transformers across a power grid, which geophysical modeling suggests is physically possible during a sufficiently severe geomagnetic storm, would not produce a temporary blackout. It would produce a blackout measured in months, during which the grid itself could not be restored because the equipment needed to restore it requires the grid to already be functioning. This is not a fringe scenario. NOAA's Space Weather Prediction Center notified airlines, NASA, the Federal Aviation Administration, the Federal Emergency Management Agency, the North American Electric Reliability Corporation, and other critical infrastructure operators ahead of the January 2026 storm. FEMA, the organization responsible for national disaster response. The people who handle hurricanes and earthquakes were on the notification list for a solar storm. That is not a bureaucratic formality. That is an acknowledgement that the intersection of a major geomagnetic event and modern infrastructure is a category of disaster that requires federal emergency coordination. The fact that the January 2026 event produced northern lights visible across much of the populated world and relatively limited infrastructure damage is a function of luck. The CME arrived with a magnetic field orientation that was moderately favorable, and the timing meant many industrial systems were not at peak operational load. Different orientation, different timing, different outcome. CNN. The aurora itself is the most visible and most misunderstood aspect of what the sun sends toward Earth. Space weather forecasters indicated that a glancing CME blow could trigger geomagnetic storm conditions and boost the likelihood of spectacular aurora displays, with the northern lights potentially visible across high latitudes and in regions not typically associated with such celestial shows. What produces the aurora is this: the same energetic particles that threaten satellites and astronauts and power grids, when they follow magnetic field lines down into the upper atmosphere, collide with oxygen and nitrogen atoms at altitudes between 100 and 300 kilometers. Those collisions excite the atoms electronically, and when they relax, they emit light. Green is excited oxygen at around 100 kilometers. Red is excited oxygen at higher altitudes. Blue and purple are nitrogen. The curtains and arcs and rays are not random. They trace the structure of Earth's magnetic field, which itself is being distorted and energized by the arriving CME. The aurora is a readout. It is the planet's magnetic field making itself visible by consuming incoming solar plasma. Daily galaxy. What is happening over the poles during a major geomagnetic storm is not just beautiful. The same ionospheric currents that produce the aurora also disrupt GPS signals. Not because the satellites are damaged, but because the ionosphere through which GPS signals must travel becomes turbulent and refractive in ways that introduce positioning errors. During severe storms, GPS accuracy degrades from meters to tens of meters or more, which matters enormously for precision agriculture, autonomous vehicles, aviation instrument approaches, and military navigation. HF radio communications, which airlines and maritime operations rely on over polar routes where satellite coverage is limited, are disrupted by radio blackouts on the sunlit side and by ionospheric absorption on the night side. The X-flares in April 2026 were preceded by a flurry of M-class solar flares, triggering radio blackouts ahead of the Artemis II launch, with a powerful X-class flare triggering a radio blackout and raising concerns about the mission timeline. The Artemis crew preparing to go to the moon were watching solar weather forecasts the way sailors watch hurricane tracks. Space.com Solar Energetic Particle Events, SEPS, represent the radiation hazard that is least discussed in popular coverage and most concerning to space medicine professionals. When a major flare accelerates protons to a significant fraction of the speed of light, those protons arrive at Earth within 30 minutes of the flare, far faster than the CME that follows hours or days later. The dose rate from an intense SEP event in low Earth orbit can reach tens of millisieverts per hour. The annual occupational radiation limit for workers in nuclear facilities is typically 50 millisieverts per year. A severe SEP event can deliver that annual limit in a few hours. For astronauts on a lunar mission, beyond the protection of Earth's magnetosphere, which deflects most of the lower energy particles that reach Earth orbit, the exposure in an unshielded location would be lethal within hours during the most extreme events. The January 2026 event reached S4 severity, which implies proton flux levels that would require any astronauts in deep space to shelter in pre-prepared radiation-hardened sections of their spacecraft and hope the storm passed before accumulated dose became critical. The deeper physics of what the Sun is actually doing during these events, not the observable effects but the underlying dynamics, involves processes that occur on scales that make them practically impossible to directly observe. The corona, the Sun's outer atmosphere, is millions of degrees hotter than the photosphere below it, which violates the naive expectation that temperature should decrease with distance from the energy source. The mechanism of coronal heating, Alfvén waves, nanoflares, magnetic reconnection, some combination, has been studied for decades and remains incompletely resolved. The corona is the region from which CMEs are launched, and the lack of complete understanding of coronal dynamics is part of why space weather forecasting remains imprecise. We can detect a CME leaving the Sun. We can track it through the interplanetary medium with coronagraph images. We can model its speed and direction and arrival time with useful accuracy. What we cannot reliably predict from current observations is the magnetic field orientation of the CME when it arrives, the southward versus northward component that determines whether the event will produce a minor disturbance or a catastrophic geomagnetic storm. That determination waits until the CME is approximately 15 to 60 minutes from Earth, when sensors at the L1 Lagrange point, roughly 1.5 million kilometers sunward of Earth, first measure the actual field direction. 15 to 60 minutes to prepare for an event that could last days. The scale of the Sun's energy output during these events sits in a category that resists intuitive comparison. The X8.1 flare of February 1, 2026, released energy equivalent to roughly 10 billion hydrogen bombs detonating simultaneously. The associated CME expelled several billion tons of plasma at speeds between 500 and 2,000 kilometers per second. That plasma, when it reaches Earth, interacts with a magnetic field that protects the entire biosphere from both solar wind erosion and cosmic ray bombardment. Without Earth's magnetosphere, maintained by the planet's internal dynamo, itself powered by the slow solidification of the iron inner core, the solar wind would gradually strip the atmosphere the way it stripped Mars's atmosphere over geological time after Mars's core cooled and its magnetosphere collapsed. The auroras are therefore not just beautiful and not just dangerous. They are a visible sign of the collision between the force that would strip away the conditions for life and the planetary field that has, for 4 billion years, absorbed that force and deflected it. The current solar cycle's activity level has pushed space weather research and preparedness to a visibility that was lacking through the quiet years of Cycle 24. Government agencies in the United States, European Union, United Kingdom, and Japan have updated their space weather preparedness frameworks. Power grid operators have installed GIC monitoring equipment that was not present a decade ago. Some transformer manufacturers have begun adding geomagnetic protection to new units. The problem is that the existing infrastructure, the transformers already in the ground, the satellites already in orbit, the GPS receivers already embedded in every critical system, was built before these standards existed and cannot be retroactively upgraded easily or cheaply. The grid that runs most of North America contains transformers that are 30, 40, 50 years old, designed to specifications that did not include severe geomagnetic storm resilience, serving a population that has become more dependent on uninterrupted electricity than any previous generation in history. What the Sun released toward Earth in January 2026, and again in February, and again in May, was not unusual from the perspective of stellar physics. The Sun does this. It has been doing this for 4.5 billion years. The Carrington event of 1859 was stronger than anything in the current cycle and produced no major infrastructure damage. Because in 1859, there was no major infrastructure to damage. Telegraph systems caught fire and operators received electric shocks, which was spectacular and dangerous, but the event did not threaten civilization's functional continuity. The same event today would be categorically different in its consequences, not because the Sun is more violent, but because we have constructed a global civilization whose operation depends on systems that the Sun can disrupt. The Sun has not changed. We have. Here is something that almost nobody thinks about when they watch a news segment about a solar storm. The light you see right now, the ambient light coming through your window, the screen in front of you, the lamp in the corner, every photon of it originated as a gamma ray in the Sun's core around 100,000 years ago. It spent most of that time bouncing around the radiative zone, being absorbed and re-emitted billions of times, slowly diffusing outward. Then it spent about 8 minutes traveling from the solar surface to your eye. That journey took 100,000 years and 8 minutes, and you have never once thought about it. Now consider that the coronal mass ejection currently traveling toward Earth at 2,000 kilometers per second took about 2 days to get here, and it contains enough magnetic energy to rearrange the current that flows through every transformer in North America simultaneously. The photons took longer. The CME did more damage. This is not a metaphor for anything. It is just the Sun being the Sun, and the Sun does not care about the distinction. The thing that space weather scientists find genuinely difficult to communicate is not the danger. Danger is easy to communicate, sometimes too easy, and the public oscillates between panic and indifference depending on whether auroras showed up visible from their city. What is difficult to communicate is the combination of randomness and scale. A CME heading directly toward Earth is not a targeted attack. It is not a pattern. The Sun does not aim. It erupts in directions determined by the local geometry of its magnetic field lines in a specific active region at a specific moment. And whether that eruption happens to be pointed at the third planet from the star is essentially a matter of geometry and timing. Most CMEs miss. A significant fraction graze. A small fraction hit directly. Among those that hit directly, whether the magnetic field orientation is favorable or catastrophic is determined at the last minute, literally, in terms of forecasting time. The people running power grids and satellite operations are making their decisions based on data arriving roughly 30 minutes before impact, and that data tells them the field orientation for the first time. Everything before that is educated extrapolation with significant uncertainty bars. January 19, 2026 is worth examining in some detail because it is the most recent case where a G4 event hit Earth's infrastructure at meaningful scale, and the response, while ultimately managing to avoid catastrophe, revealed how close the margin actually was. The CME hit earlier than forecast. This is important. Space weather models predicted arrival within a window of several hours, and the actual arrival came ahead of the early edge of that window, which meant some operators who had been told they had time to prepare did not have that time. Airlines had already diverted polar routes. Satellite operators had already put spacecraft into safe mode. Power grid operators in North America and Europe had already reduced transmission loads on vulnerable long-haul lines. These precautions worked, partly because they were taken, and partly because the storm's magnetic field, while southward and therefore geo-effective, did not stay in its worst orientation for the longest possible duration. Had the field remained at peak southward orientation for 6 or 8 hours instead of the actual duration, the GIC levels in long transmission lines would have been significantly higher, and the probability of transformer saturation and thermal damage would have risen substantially. The preparedness community ran the models afterward. The margin was not comfortable. Auroras during a G4 event are visible from latitudes that have no business seeing them by any normal standard. During the January storm, reliable reports of naked-eye aurora came from Texas, from northern Spain, from southern France, from Japan. Not the faint greenish glow that dedicated aurora chasers photograph with long exposures. Actual, visible light, visible to the unaided eye, moving, structured, in colors that depend on the altitude and the atmospheric composition at that altitude. The reds that appear at high altitude, excited oxygen above 200 kilometers, are the sign of a particularly energetic event, because lower energy storms only excite the oxygen at lower altitudes where the green emission dominates. A sky full of red aurora over a European city means the magnetosphere is being compressed and energized to a degree that is simultaneously spectacular and worth taking seriously as an infrastructure warning. Medieval Europeans who saw these lights over their cities during the historical storms that accompanied what we now call the medieval maximum of solar activity interpreted them as blood in the sky, as divine warning, as the reflection of burning cities over the horizon. They were not entirely wrong about the warning part, just wrong about the mechanism. The X8.1 flare of February 1, 2026 deserves particular attention not because it was the most dangerous event of the current cycle, but because of what it represents structurally. X-class flares are the most powerful category in the standard classification system. Within the X-class, the number after the letter gives the relative intensity. X1 is 10 times more energetic than M10, X2 is twice X1, and so on. X8 means the event was roughly 80 times more powerful than the threshold for the X classification. The largest flare ever recorded by modern instruments was the X28 of November 4, 2003. So large that it went off the top of the measurement scale, and the X28 designation is an extrapolation. The X8.1 of February 2026 was in the top tier of observed events outside that historical outlier, and it was accompanied by 4 other X-class flares from the same active region within days. Multiple X-class flares from a single active region in a short window is a signature of a region with extraordinary stored magnetic energy, where each reconnection event releases tension, but the underlying field configuration remains stressed enough to produce another major release within hours or days. The sunspot group responsible was described by forecasters as magnetically complex in a way that made continued extreme activity not just possible, but expected. Space weather forecasting as a discipline sits in an uncomfortable position between meteorology and geophysics, and is less mature than either. The National Weather Service has over 100 years of ground-based observation data, sophisticated ensemble modeling, and continuous improvement in forecast skill. NOAA's Space Weather Prediction Center has a few decades of satellite observation, models that are improving but nowhere near the skill of terrestrial weather prediction, and a physical problem that is in some ways harder. The sun's interior dynamics are not directly observable. The propagation of a CME through the complex solar wind is difficult to model with high fidelity, and the key parameter for impact severity, the magnetic field orientation at arrival, cannot be measured in advance by any current technology. There are proposals for spacecraft that could sit further sunward at L5, the trailing Lagrange point, and potentially give earlier warning of field orientation as CMEs pass that point before reaching L1. But those spacecraft do not yet exist as operational assets. ESA has plans. NASA has proposals. Meanwhile, the forecasting window remains what it has always been. The economic dimension of this is not often discussed in scientific coverage because it feels crass to put a dollar figure on a stellar plasma ejection. But the numbers are worth knowing. A single large power transformer, the kind that steps voltage down for regional distribution, costs between $3 million and $10 million, weighs up to 800 tons, requires specialized manufacturing equipment that exists in only a handful of facilities globally, and takes 18 to 36 months to manufacture and deliver. There are roughly 2,000 of these units on the North American high-voltage grid. A Carrington-level event could in principle damage a significant fraction of them simultaneously. The replacement cost alone, before counting the cascading economic damage from months of widespread power outage, runs into hundreds of billions of dollars. The economic analysis firm Lloyd's of London produced an estimate suggesting a severe space weather event could cost the United States between $0.6 and $2.6 trillion in the first year alone. For context, the 2008 financial crisis cost roughly $10 trillion over several years. A geomagnetic catastrophe would be shorter in onset and, in some respects, more severe in immediate physical terms. Hospitals losing power, water treatment plants failing, fuel distribution collapsing. The sun, operating normally within its documented cycle, has the theoretical capacity to produce that. What is genuinely strange about the sun from a physics standpoint is not that it produces these events. It is that the mechanism producing them is powered by processes that operate across vastly different scales simultaneously. The nuclear fusion in the core proceeds through quantum tunneling, the same quantum effect that lets electrons pass through barriers in semiconductors. Except here, it lets protons come close enough to fuse despite their mutual electrostatic repulsion. Without quantum mechanics, the sun would not burn, because classical protons do not have enough thermal energy to overcome the Coulomb barrier at solar core temperatures. The energy released in fusion takes 100,000 years to diffuse to the surface. Then, surface convection, turbulent boiling columns of plasma visible as granulation through solar telescopes, organizes magnetic field lines over hours to days. Then, magnetic reconnection in the corona releases that stored energy in minutes. Then, the particle acceleration along reconnecting field lines happens in seconds. Then, the CME travels through space for 1 to 3 days. Then, it interacts with Earth's magnetosphere over hours. Then, ionospheric currents induced by the storm affect GPS signals and power grids over timescales of minutes to hours. 6 separate timescales ranging from 100,000 years to minutes, all mechanically connected through physics that operates continuously without stopping. The sun is a system that processes energy on geological time and delivers it to Earth in electromagnetic pulses measured in minutes. And every stage of that process is running right now, has been running since the planet formed, and will keep running for another 5 billion years. Solar cycle 25's overperformance relative to predictions is interesting for what it says about solar forecasting as a science. The consensus prediction released before the cycle began, developed by a panel of expert scientists, suggested the cycle would be weak to moderate, similar to the quiet cycle 24, which was notably below historical averages. Instead, cycle 25 became one of the most active in the satellite observation era. This is not a trivial forecasting error. It is a fundamental prediction failure about the basic behavior of a well-studied system. And it happened because the physical processes driving solar activity cycles are not fully understood. The 11-year cycle is produced by the interaction between differential rotation. The equatorial solar surface rotates faster than the poles, which shears and stretches magnetic field lines, and the deep convective transport of magnetic flux by large-scale meridional flows. The interplay of these processes determines when and how violently the stored magnetic energy releases. The models that predicted a quiet cycle were working with the same physics, but apparently with systematic errors in how they were parameterized. Whether those errors have been identified and corrected, and whether forecasts for future cycles will be more accurate, is genuinely unknown. The sun humbled the experts who study it most closely, and the lesson that space weather has the capacity to surprise in the upward direction, to be worse than expected rather than better, is one the relevant agencies have taken seriously in their recent preparedness planning. The social dynamic around major solar events is one of the stranger aspects of the modern relationship between science and public communication. When the January 2026 storm produced northern lights visible from Texas and Spain and Japan, social media filled with photographs of extraordinary beauty, with people standing in their backyards in winter clothes looking at something they had never seen and might never see again. The framing was celebration. The framing was wonder. The framing was nature doing something remarkable, all of which is true. Simultaneously, power grid operators were staring at monitoring dashboards, watching GIC levels approach thresholds they had not seen in decades. Satellite operators were sweating over spacecraft in unplanned safe modes, and aviation regulators were routing flights around polar regions that were suddenly bathed in high-energy particle flux. Both things were happening at the same time. The beauty and the hazard were the same phenomenon. The same plasma wave that made the sky over Dallas glow green was inducing voltage spikes in transmission lines across 3 time zones. This dual nature is not unusual in physics. Most energetic natural phenomena produce both destruction and spectacle. But the contrast between the Instagram feeds and the control room monitors during a G4 event is stark in a way that probably deserves more direct public acknowledgement than it typically receives. The question of whether we are in a period of genuinely elevated solar activity relative to historical norms, not just relative to the quiet years of cycle 24, is one that solar physicists approach carefully. Ice cores and tree rings preserve records of large historical solar energetic particle events through the cosmogenic isotopes those events deposit, primarily beryllium-10 and carbon-14. These records go back thousands of years. They reveal that the Carrington event of 1859, long considered the benchmark extreme event of the modern era, was not unique historically. There appear to have been events of similar or greater magnitude roughly once every few centuries across the last several thousand years. There is also evidence for what are called grand maxima, extended periods of elevated solar activity lasting decades to centuries, and grand minima, like the Maunder minimum, when sunspot activity nearly ceased for roughly 70 years during the 17th century, correlating with a period of anomalously cold climate in the northern hemisphere. Whether we are currently in or approaching a grand maximum is debated. The current cycle's overperformance is one data point. It is not by itself conclusive. but it is a data point in a direction that should focus attention rather than allow complacency. Satellites are in some ways the most immediately vulnerable class of infrastructure during major solar events, and the public relationship with satellites is one of quiet dependence without awareness of fragility. Every weather forecast on your phone relies on satellite data. Every GPS position fix relies on satellite signals. Much of the internet relies on satellite backhaul in regions without fiber. Financial transactions rely on satellite-based time synchronization. Television, search and rescue, maritime navigation, precision agriculture, military targeting. The list of functions that depend on satellite infrastructure is so long and so embedded in the background of modern life that most people have no direct experience of any of it, and therefore no visceral sense of what its disruption would mean. Satellites in low Earth orbit experience increased atmospheric drag during geomagnetic storms because the storm heats the upper atmosphere, causing it to expand outward and increasing drag at orbital altitudes. This causes satellite orbits to decay faster than normal, requiring operators to fire thrusters more frequently to maintain altitude, and for satellites without propulsion to re-enter sooner than scheduled. The February 2023 destruction of 40 Starlink satellites, lost shortly after deployment when a geomagnetic storm caused unexpected atmospheric density at their operational altitude, was a preview at small scale of a larger vulnerability. There is a category of solar event that makes everything described so far look modest. A solar superflare, a flare roughly 10 to 1,000 times more powerful than the largest events observed in the current cycle, has been observed from other sun-like stars. The statistical frequency of superflares on solar-type stars can be estimated from the Kepler and TESS missions, which have observed thousands of stars over long baselines. The data suggests that superflares of roughly 10 times the Carrington magnitude occur on sun-like stars approximately once per 1,000 years. Whether our sun is capable of such events is debated. The sun's relatively slow rotation compared to some active superflare stars is sometimes cited as a reason to think it may be less capable of the extreme magnetic field configurations needed. But the historical cosmogenic isotope record contains at least two events, the 775 AD and 994 AD events, whose isotopic signatures are roughly 10 times larger than the Carrington event signature, suggesting they were caused by solar energetic particle events of a magnitude that has no modern analog. The Sun has apparently produced events in the last 1,500 years that would be categorized as extreme by any current standard, and those events occurred long before any infrastructure existed that could be damaged. The Sun's documented historical behavior includes events that would be civilizationally disruptive if they occurred today. That is not speculation. That is what the ice cores say. The current generation of space weather researchers is the first to have continuous, real-time monitoring of the Sun from multiple spacecraft simultaneously. SOHO, ACE, WIND, STEREO, Solar Orbiter, Parker Solar Probe, DSCOVR, along with a global network of ground-based magnetometers, ionospheric sensors, and cosmic ray detectors. Parker Solar Probe, which has been making close approaches to the Sun at distances closer than any previous spacecraft, has sent back data from within the corona itself, measuring the magnetic field and particle environment in the region where CMEs originate. This is fundamentally new information. The models being built from Parker data are beginning to describe the coronal magnetic field in ways that were previously impossible. And the hope is that within a solar cycle or two, CME forecasting will improve to the point where the magnetic field orientation at arrival can be predicted hours rather than minutes in advance. Whether that timeline is realistic is uncertain. The sun, as the current cycle has demonstrated, has a way of overperforming against expectations, and the relationship between better observation and better prediction is not always linear when the underlying system is as complex as the solar corona. What the sun released toward Earth in the past year, repeatedly, in events that ranged from radio blackouts to the most powerful radiation storm in recorded satellite history, was a reminder that the planet does not exist in a stable, benign cosmic environment. It exists in the habitable zone of an active variable star that is currently near the peak of an activity cycle, and that star continuously sends energy and material in all directions, some of which hits Earth. The magnetosphere deflects most of it. Some gets through. During major events, enough gets through to disrupt the electromagnetic infrastructure that modern civilization depends on, sometimes severely. The people studying this, the space physicists, the space weather forecasters, the grid engineers, the satellite operators, are working in a domain where the stakes are extremely high and the public visibility is extremely low, and where the gap between understanding the threat and communicating it effectively remains one of the persistent failures of the science-society interface. The sun will keep erupting. The infrastructure will keep being vulnerable. The question of whether the preparation matches the risk is one that gets a new data point every time another CME detaches from an active region and begins its 2-day journey toward the third planet from the star. One of the stranger things about living on Earth during a major solar storm is that the event is simultaneously happening everywhere on the planet and nowhere most people can detect it. During the January 2026 G4 storm, a person standing in a field in Kansas at the right moment could look north and see the sky doing something it has no business doing. Green curtains, red pillars, things that move. A few hundred kilometers away, a power utility engineer was watching GIC readings on a monitor climb toward levels she had only seen in historical records and training scenarios. And she was on the phone with a grid coordinator making real-time decisions about load management that would affect whether millions of people kept their lights on. Both of those people were experiencing the same event. Neither was aware of the other's experience. And somewhere above both of them, at 400 kilometers altitude, the astronauts on the International Space Station were in the most shielded module they had, watching dosimeters, waiting for the particle flux to come down, acutely aware that the atmosphere below them, which normally provides a comfortable radiation buffer, was being actively compressed by the same plasma wave that was making the Kansas sky do impossible things. The ISS experience during major solar events is genuinely strange from a human perspective, and the astronauts who have described it talk about it in ways that are hard to categorize as either routine or frightening. The procedure is established and rehearsed. Move to the shielded module, monitor dosimeters, maintain communication with mission control, wait. But the thing you are waiting for is the magnetosphere of your home planet, which you can currently see as a blue sphere below you, to absorb enough of the incoming plasma that the particle flux at your altitude drops to safe levels. You are watching Earth handle something on your behalf. The planet is actively protecting you, not through anything you built, but through the same magnetic field that has been performing this function for 4 billion years, long before anything on the surface was complicated enough to be worth protecting. This is not a relationship that most people think about. The magnetosphere is invisible, and its function is invisible, and most people go through their lives without ever directly experiencing either its presence or its absence. The astronauts who have sheltered during solar radiation storms are among the small number of humans who have had reason to think about it concretely, in real time, while it was happening. The particle physics of what arrives during a severe solar energetic particle event has a detail that most popular accounts skip past because it seems technical, but is actually one of the more viscerally striking facts about these events. The protons accelerated during a major solar flare reach energies measured in hundreds of millions to billions of electron volts, giga-electron volt range. At those energies, protons are traveling at greater than 95% of the speed of light. They arrive at Earth approximately 30 minutes after the flare that produced them. The light from the flare itself arrives 8 minutes after the eruption. This means there is roughly a 20-minute window between when you can see the flare and when the first relativistic protons arrive. 20 minutes is not much time to do anything, and at current detection capability, it is barely enough to issue a warning, let alone take most protective actions. The CME that accompanies the flare takes 1 to 3 days to arrive, the slow freight that carries the bulk of the plasma. But the relativistic protons are the express. They travel at 95% of light speed, and they do not wait. When NOAA's instruments at L1 detected the January 2026 event's particle flux beginning to rise, the warning that went out to polar aviation and satellite operators had a lead time measured in minutes. The sun's magnetic poles reverse every 11 years at solar maximum. This is not a metaphor or an analogy to Earth's magnetic field. It is a literal reversal of the solar magnetic dipole, driven by the same dynamo processes that create the sunspot cycle. During the reversal, which is currently happening as cycle 25 peaks, the sun's global magnetic field passes through a disordered intermediate state where the simple north-south dipole breaks down into a more complex multipolar configuration before re-establishing an opposite polarity. This transition period is associated with increased complexity in active region magnetic configurations, which is associated with increased probability of major flares and CMEs. The current period of peak solar activity is therefore not just about the sunspot count being high. It is about the underlying global magnetic field being in a transitional state that specifically favors the kinds of magnetically complex active regions that produce extreme events. The sun is not just active. It is structurally in a configuration that promotes the exact type of activity that threatens infrastructure. Watching a solar flare from Earth's surface, not the eruption itself, which requires satellite X-ray detectors or solar telescopes, but its effects, involves noticing things that seem completely unrelated and then realizing they are connected. During the February 2026 flares, amateur radio operators across North America noticed that their signals, which had been propagating cleanly at certain frequencies, suddenly faded within 8 minutes of the flare peak. That 8-minute fade is the electromagnetic signal from the flare traveling at light speed, hitting the ionosphere and increasing its electron density on the sunlit side to the point where HF radio waves are absorbed rather than reflected. The radio operators who track these fade events in real time are, without necessarily thinking of it this way, using their receivers as light speed detectors of solar flare events. The fade happens simultaneously across the entire sunlit hemisphere of Earth, from the American Southwest to Europe to Central Asia, all at the same moment, because the light traveling from the sun hits all of them at the same time. A global, simultaneous event, detectable by anyone with an HF radio, happening in plain sight without most people knowing it is happening. The Carrington event of 1859 is the standard reference point for extreme solar weather, and it has been used so many times in popular science articles that the details have become somewhat blunted through repetition. But some of the specifics deserve to be stated plainly. The event was not one flare and one CME. It was a period of intense activity, with the most extreme CME arriving on September 1st and 2nd, preceded by a less severe event that had partially cleared the solar wind ahead of it, allowing the main CME to travel faster than it otherwise would have through the reduced drag. This is a phenomenon called a preconditioning event, and it amplified the impact of the primary CME beyond what it would have produced traveling through an undisturbed solar wind. The auroras during the main storm were visible from the Caribbean. In September, from Cuba and Colombia and Hawaii, latitudes where the equatorial electrojet normally prevents aurora visibility entirely. Telegraph operators who had gone home for the night found their systems operating spontaneously, powered by geomagnetically induced current, before the systems themselves caught fire from the induced voltage spikes. The storm lasted several days. The global magnetic disturbance was so severe that compass readings were unreliable across entire continents for hours at a time. If you are trying to understand the scope of what the Carrington event would mean today, do not think about it in terms of the technology it affected in 1859. Think about what it did to electromagnetic fields, and then map that onto modern infrastructure that has no equivalent protection from the same field changes. The story of how space weather became a recognized national security concern in the United States is shorter and more recent than most people expect. For most of the 20th century, solar weather was treated as an interesting geophysical phenomenon, studied by academics and of operational concern to radio operators and some satellite engineers. The 1989 Quebec blackout, when a geomagnetic storm collapsed the Hydro-Quebec power grid in 90 seconds, cutting power to 6 million people for up to 9 hours and causing transformer damage as far south as New Jersey, began to change that. The Halloween storms of 2003 accelerated it. A 2008 National Academy of Sciences report explicitly described a severe geomagnetic storm as capable of causing societal and economic disruption that would require years to recover from, which was the first time the scenario had been articulated at that level of institutional authority. Executive orders followed. NOAA upgraded its Space Weather Prediction Center. The Department of Homeland Security added space weather to its hazard planning frameworks. But the gap between recognizing the threat and hardening the infrastructure that faces the threat has remained substantial. Because hardening old transformers and upgrading old transmission lines costs enormous amounts of money and competes for budget with threats that feel more immediate, even if they are statistically less damaging. There is a version of the solar storm story that almost never gets told, which is the version from the perspective of the sun. Obviously, the sun has no perspective. It is a plasma object, not a conscious agent. But try to think about what the event looks like from outside, as a physical process. The sun has been in this configuration, this particular arrangement of magnetic flux tubes threading through its outer layers, this particular distribution of active regions, this particular phase of its magnetic cycle, for approximately 11 years. The dynamo process that drives the cycle has been running, continuously, for 4.5 billion years. The current solar maximum is the 400 and some millionth solar maximum in the history of the sun. Most of those occurred before there was anything on the third planet worth disrupting. For almost all of the sun's history, the CMEs it launched were received by planets with no infrastructure, no electrical grids, no communication networks, no GPS. Just rock and atmosphere and, for the last small fraction of the timeline, biology. The biology was affected by geomagnetic storms. There is evidence that magnetoreceptive animals like migratory birds show behavioral disruption during severe geomagnetic events, but not in ways that threatened civilizational continuity. The window in which human civilization is both technologically dependent on electromagnetic infrastructure and not yet technologically capable of fully protecting that infrastructure from solar weather is narrow by geological standards. We are in that window right now. The sun does not know this and would not care if it did. The rate at which Parker Solar Probe data is changing the understanding of coronal mass ejections is worth dwelling on for a moment, because it represents one of the genuine frontiers of space physics happening in real time. Parker has made numerous close approaches to the sun, getting within about 11 solar radii at its closest, closer than any previous spacecraft by a significant margin. At those distances, it is flying through the solar corona itself, the region where CMEs originate and where the solar wind is first accelerated. The magnetic field measurements Parker has returned have revealed structures in the corona, sharp reversals in field direction called switchbacks, which appear as spikes in the solar wind radial velocity that were not predicted by existing models and whose origin and significance are still being worked out. The heating mechanism of the corona, the long-standing puzzle of why the corona is millions of degrees hotter than the photosphere below it, is beginning to look like it may involve the energy carried by these switchbacks and by alvanic waves propagating from the surface. This matters for CME prediction because understanding how energy is stored and released in the corona is the prerequisite for understanding when and how violently CMEs will occur. Parker is providing data that makes the models less wrong, which is how science proceeds. But the improvement in forecast skill that scientists hope will follow from better physical understanding has not yet fully materialized in operational forecasting. The sun remains, in the most practical sense, ahead of our ability to predict its behavior. What the current solar cycle has produced, beyond the individual events, is a renewed sense among space weather researchers that the operational baseline for major events, how often severe storms happen, how severe they typically are, may have been systematically underestimated based on the quiet years of cycle 24. If cycle 24 was anomalously quiet, and cycle 25 is closer to historical norms, then the preparedness frameworks built during the cycle 24 period may have been calibrated to a level of activity that is not representative of what the sun normally does. This would mean that the frequency and severity of events that grid operators, satellite manufacturers, and aviation authorities need to plan for is higher than their current planning assumptions. It does not mean the sky is falling. It means the baseline was probably set too low, and adjusting it requires changing engineering standards, operational procedures, and budget allocations that were built on the previous baseline. That process is slow and contentious and expensive, and it is happening in the background of a solar cycle that is not waiting for the institutional adjustment to catch up. The next major event is a matter of when, not if. The sun has regions of magnetic complexity that forecasters are currently monitoring. The transition from solar maximum to solar minimum is gradual and irregular, and the strongest individual events in a cycle sometimes occur on the descending slope after the peak. Every day that passes without a severe geomagnetic storm is a day in which the probability of one occurring tomorrow is essentially unchanged. The sun does not remember how long it has been quiet. The infrastructure that faces the threat is the same infrastructure it was before the January storm, before the February flares, before the May events. Some operators have taken additional precautions. Some haven't. Some transformers that were old and vulnerable in January are still old and vulnerable now. The aurora will appear again over latitudes that don't normally see it. The radio operators will notice their signals fade. The ISS crew will move to the shielded module. The GIC monitors in the control rooms will climb toward thresholds. And most people, looking up at the impossibly colored sky, will take a photograph and post it without fully registering that the same wave making the sky glow was simultaneously running electrical interference patterns through the infrastructure that keeps their city running. There is a specific kind of cognitive dissonance that space weather scientists describe when they try to explain their work to people outside the field. They are studying the most powerful object in the solar system, something that produces events releasing the energy of billions of nuclear weapons simultaneously. Something that can disrupt global infrastructure in ways that have no parallel in any other natural hazard category. And the reaction they most often get is polite interest, followed by a return to whatever the person was doing before. The problem is not that people are incapable of understanding the threat. The problem is that solar storms have no dramatic ground-level signature that triggers the survival instincts that respond to earthquakes, or hurricanes, or floods. When a major CME hits, the sky might do something beautiful if you are at high latitude and looking up at the right time. Your radio might have static. Your GPS might be slightly off. None of these things feel dangerous. The danger is happening in systems that are invisible to ordinary experience. In the magnetic field of the planet, in the ionosphere 200 kilometers overhead, in the electrical grid that is just always there doing its thing in the background. The mismatch between the actual risk profile and the experiential risk profile is one of the reasons that the preparedness for this category of hazard lags so far behind the preparedness for hazards that feel dangerous when they happen. The biology of solar storms is a topic that gets far less attention than the physics, and there are aspects of it that are genuinely surprising. Migratory birds use Earth's magnetic field as a compass. There is strong evidence that this magnetoreception is mediated by quantum entanglement in cryptochrome molecules in the bird's retina, exactly the kind of quantum biological effect discussed in quantum biology literature. During a severe geomagnetic storm, the magnetic field that the birds are navigating by is being actively disrupted by the arriving CME. Field lines that normally point reliably north are being compressed and distorted and temporarily reversed in orientation at local scales. Studies of bird populations during major geomagnetic events have found evidence of disorientation, altered migration routes, and increased collision rates with obstacles. This is not a catastrophic effect. Birds have been navigating through geomagnetic storms for as long as both birds and solar storms have existed. But it is a direct biological consequence of the same event that is disrupting radio communications and power grids. The same plasma wave is simultaneously confusing birds, disrupting GPS satellites, and making auroras visible from subtropical latitudes. This multiplicity of simultaneous effects across completely different scales and systems is one of the things that makes solar storms genuinely unlike other natural hazards. Marine mammals that use magnetoreception for navigation show similar disruption. Whale stranding events have been correlated with geomagnetic disturbances in a number of studies. Not perfectly. Not every stranding has a geomagnetic correlation, but the statistical signal is real enough that researchers take it seriously. The proposed mechanism is that whales following magnetic field intensity contours toward breeding or feeding grounds are being sent along paths that become invalid when the field is being actively deformed by a solar storm. The whales are following a map that is temporarily wrong. They end up in shallow water and strand. This is speculative in its mechanistic details, but the correlation is documented. It is one of the stranger ways in which a stellar ejection event 200 million kilometers away produces consequences at the surface of the Earth's oceans, involving the behavior of the largest animals alive. The human body's relationship to geomagnetic disturbances is an area where the science is genuinely contested, and where it is important to separate what is established from what is speculated. There is solid evidence that the cardiovascular system is sensitive to geomagnetic activity. Studies published in peer-reviewed journals have found correlations between severe geomagnetic storms and increased rates of acute myocardial infarction, with the proposed mechanism involving disruption of the circadian rhythm regulation that is partly mediated by light-dark cycles that are themselves affected by ionospheric changes. There is also evidence from some studies suggesting elevated rates of psychiatric emergency admissions during major geomagnetic events, though this research is less robust and the confounding factors are more difficult to control. What can be said carefully is that the human nervous system evolved in the presence of Earth's magnetic field, that the field is a background physical environment that the body has been calibrated against for millions of years, and that sharp deviations from baseline are at minimum worth studying for physiological effects. The claim that any specific mechanism has been proven is stronger than the evidence supports. The claim that there is nothing worth investigating is also stronger than the evidence supports. Plants and their relationship to space weather are even less studied and even more interesting at the margins. Trees, notably, appear to have some sensitivity to geomagnetic disturbances, with growth rate measurements showing anomalies during major geomagnetic events in studies from Finnish and Russian research groups working with long tree ring archives. The proposed mechanism is vague, possibly involving effects on the light environment through ionospheric changes, possibly involving direct effects on some aspect of cellular biochemistry sensitive to magnetic field changes. This is at the frontier of research and should be treated with appropriate uncertainty. What is less speculative is that the increased UV exposure that sometimes accompanies major solar events, because the ionosphere's UV-absorbing capacity changes during geomagnetic disturbances, has measurable effects on plant biology, particularly on plants at high altitude or high latitude, where the UV protection of the lower atmosphere is thinner. The ozone layer chemistry is affected by energetic particle precipitation during severe events, which can locally deplete ozone and increase UV surface flux. Plants at high altitude noticed this before scientists did. The damage patterns in high-altitude vegetation after major solar events are a documented phenomenon in the literature, even if the mechanism took time to establish. The historical relationship between solar activity and human civilization is one of the genuinely underexplored areas of archaeohistorical research, and what has been established is both interesting and appropriately ambiguous. The Maunder minimum, the period from roughly 1645 to 1715, when sunspot activity nearly ceased, coincided with the coldest phase of the Little Ice Age in Europe, with documented famines, crop failures, and demographic collapses across multiple European societies. The causal mechanism connecting solar minimum to cooling involves reduced total solar irradiance and possibly changes in UV output affecting stratospheric ozone chemistry, both of which are quantitatively small effects that nevertheless appear to have been amplified by the climate system through feedback mechanisms that are still being studied. The Dalton minimum of the early 19th century similarly coincided with the year without a summer in 1816, itself coinciding with the Tambora eruption. The relative contributions of the volcanic forcing and the solar minimum to that year's catastrophic cooling are debated. The Sporer minimum of the 15th century coincided with another cold period and has been proposed as a contributing factor to the demographic and economic disruptions of that era. None of these correlations amounts to proof of causation, and the effect sizes are small compared to other climate forcings. But the pattern is consistent enough that serious climate scientists take the solar irradiance variation signal seriously as a secondary forcing factor in the historical climate record. The opposite end of the solar activity spectrum, grand maxima rather than grand minima, has received less attention in this context, possibly because the medieval warm period, which correlates with elevated solar activity, is a politically charged topic in climate science. What is physically clear is that elevated solar activity produces more UV radiation and a slightly higher total solar output, and that both of these have climate effects that are modest but real. More relevant to the current discussion is that grand maxima, if the current cycle represents one, are also periods of elevated space weather risk, more CMEs, more major geomagnetic storms, more SEP events. The relationship between climate effects of solar variability and infrastructure risk from solar variability is rarely discussed together, but they are aspects of the same underlying phenomenon. A society that is adjusting to climate effects from elevated solar output is simultaneously operating under elevated space weather risk. The two timescales are different. Climate effects accumulate over decades. Space weather risk manifests in individual events, but the underlying driver is the same. The economics of space weather preparedness has a specific structure that makes it difficult to address through normal market mechanisms. The risk is low probability and high consequence, which is the category of risk that private markets systematically underprice because the probability is too low to affect immediate costs, and the consequence would fall partly on parties other than those making the investment decision. A power company that hardened its transformers against geomagnetic storms would bear the full cost of that hardening, but would capture only a fraction of the benefit, because a Carrington-level event would affect the entire interconnected grid. And the benefit of having hardened transformers would partly accrue to other utilities whose customers would be protected by the fact that the grid stayed up. This classic externality problem means that even fully rational private actors would underinvest in geomagnetic storm resilience relative to what is socially optimal. Government mandates or standards are the standard economic solution to this kind of market failure. And NERC, the North American Electric Reliability Corporation, has been developing geomagnetic disturbance standards for power grid operators. But the standards in place are not yet at the level that would provide protection against the most severe historical events in the cosmogenic isotope record. And the gap between what the standards require and what the worst-case scenario demands remains significant. The satellite industry faces a version of the same problem with a different institutional structure. Individual satellite operators make engineering decisions about radiation shielding, orbital altitude selection, and component redundancy that affect how vulnerable their spacecraft are to space weather. The better shielded spacecraft survive events that destroy less protected ones. The market for launch and satellite services does not perfectly price geomagnetic storm risk, and the consequence of a major event that destroys multiple satellites simultaneously would partly fall on users of satellite services rather than on the satellite operators themselves. Insurance markets for satellite loss exist, but do not fully internalize the correlated risk. The possibility that a single event could simultaneously damage dozens or hundreds of spacecraft across multiple operators. The SpaceX Starlink loss of February 2023 was a relatively modest preview of this correlated risk, affecting 40 satellites from one operator. A more severe event could affect spacecraft from every operator simultaneously, in a way that the insurance actuarial tables based on normal loss experience would not have priced correctly. There is something almost philosophically interesting about the position humanity occupies right now relative to the Sun. We have developed, within the last century and a half, a complete global civilization that is deeply dependent on electromagnetic systems that the Sun can disrupt. We have developed, within the last several decades, the scientific capability to understand how and why the Sun disrupts those systems. We have developed within the last decade or two the beginning of an institutional and regulatory framework for managing that risk. And we are doing all of this during a period of elevated solar activity, while the gap between what we understand and what we have actually hardened against remains large. The Sun is not doing anything new. It erupted exactly like this during the Little Ice Age, and during the medieval maximum, and during every other period of human history. The difference is that now the eruptions have consequences that they did not have before. Not because the Sun changed, but because we built things that the Sun can break. We invented the vulnerability. We built it into every electrical outlet and every satellite and every GPS chip. And now we are in the position of trying to retrofit resilience into systems that were never designed with the Sun's behavior in mind, fast enough to stay ahead of a star that is, in the current cycle, operating at a level that consistently exceeds the predictions of the people who study it most carefully. The psychological dimension of living with this kind of background risk is one that almost nobody discusses, and that probably deserves more attention than it gets. The space weather community has been trying to communicate this risk for decades. The Carrington event scenarios get dusted off whenever a major storm occurs, and then put away again when the storm passes without grid collapse. The cycle of alarm and reassurance has probably damaged the community's credibility with a public that has been told multiple times that a devastating solar superstorm is possible, and then watched events that were described as severe produce nothing worse than beautiful auroras and temporary radio static. The actual severe impacts, the diverted flights, the stressed grid operators, the satellite anomalies, happen in systems that are invisible to most people, and the people managing those systems do not typically give press conferences about how close the margins were. This visibility asymmetry means the public narrative around solar storms consistently underrepresents the actual severity of the events that have already occurred. The January 2026 storm was, by objective measures, one of the most significant space weather events in decades. Most people who were alive during it know it primarily as the time the northern lights were visible from places that don't normally see them. The deep time perspective on all of this is the one that is hardest to hold on to, but most illuminating. The sun has been ejecting plasma at the planets of this solar system for 4.5 billion years. For almost all of that time, the only response from Earth was aurora, geomagnetic disturbance, and perhaps some disruption to the navigation of magnetoreceptive animals. The window in which any of this matters to anything that can be disrupted, in which the sun's behavior has civilizational consequences, is perhaps 200 years old at the outside, and realistically much less than that for most of the infrastructure at risk. The sun is doing what it has always done. The grid is new, the satellites are new, the GPS is new. The assumption of continuous electromagnetic normalcy that underpins modern civilization is new. The star is not accommodating the infrastructure. The infrastructure arrived in the star's neighborhood and is now navigating the star's behavior. Whether it does so successfully depends on decisions being made right now, in research programs and regulatory frameworks and engineering standards and budget allocations, by people who are mostly working without adequate public attention or institutional urgency, on a problem that the sun will test again on a timeline it has no reason to vary. The ongoing solar activity in May 2026, with the M5.7 flare and associated CME from May 10th, the continuing monitoring of active regions, the forecasters watching sunspot group AR4436 as it dominated the flare production through mid-May, is the continuation of a cycle that has been running hotter than expected since it began. The infrastructure it is testing is the same infrastructure that was tested in January and February. Some of it is better prepared than it was. Most of it is the same. The sun is not less active because we have better monitoring of it. The forecasters are better at detecting what is coming. They are not yet significantly better at preventing what arrives from having the effects it would otherwise have. The northern lights will appear again. The radio blackouts will happen again. The grid operators will be on the phone with each other again, watching monitors, making real-time decisions about systems whose vulnerability to the star they orbit has never been fully resolved, and whose protection remains one of the underappreciated engineering challenges of the age we are currently living through. The people who actually run space weather operations, not the researchers, not the policy people, the actual forecasters sitting at terminals in Boulder, Colorado, and Bracknell, England, and Tokyo and Moscow, watching real-time data streams from spacecraft and ground magnetometers, have a relationship with the sun that is difficult to describe to someone outside the job. They watch it continuously, around the clock, in shifts, the way air traffic controllers watch radar screens or emergency dispatchers watch incoming call queues. The sun is their patient and their adversary and their subject simultaneously. They know its active regions by their NOAA numbers and their magnetic classifications. They watch sunspot groups rotate across the disk over the 14 days they face Earth, tracking the evolution of magnetic complexity, looking for the signatures that precede major events. They issue forecasts that nobody reads until something goes wrong. And when something goes wrong, they are suddenly the most important people in a chain of notifications that runs from their terminals to airline operations centers and satellite control rooms and national grid coordinators and emergency management agencies. The job requires holding two things simultaneously: the routine of continuous monitoring and the knowledge that on any given day the routine might become something else entirely. The January 2026 event was not a surprise in the sense that a major CME had been detected and its Earth-directed trajectory confirmed before arrival. It was a surprise in the sense that it arrived earlier than forecast and at a severity level that pushed to G4 faster than the models had indicated. Forecasters described it later as a reminder that the uncertainty bars on their predictions are real, and that when the bars go in the wrong direction, the consequences are immediate. The question of what a truly extreme event would actually look like, not G4, not even a repeat of Carrington, but the kind of event that the 775 AD cosmogenic isotope record implies, is one that space weather scientists have modeled, but that most of the relevant infrastructure communities have not fully incorporated into their planning. The 775 AD event, detected through carbon-14 and beryllium-10 anomalies in tree rings and ice cores from multiple continents, appears to have been a solar energetic particle event, perhaps 10 times more intense than the Carrington event in terms of particle flux. This is not a theoretical maximum. It is a documented historical occurrence, which means it is within the demonstrated capability of the Sun to produce. An event of that magnitude today would not produce a temporary grid disruption. It would produce a scenario where the damage to satellite electronics, high-voltage transformers, and ionospheric-dependent communication systems was severe enough that the recovery timeline would be measured in months to years rather than hours to days. The satellites that handled GPS would be among the most vulnerable. They operate in the highest radiation orbital environment and would receive doses from a 10 times Carrington SEP event that their shielding was not designed to survive. GPS-dependent systems would fail not temporarily but permanently until replacement satellites could be manufactured, launched, and commissioned. A process that takes years under normal circumstances and would take considerably longer if the industrial infrastructure supporting it had itself been disrupted. What is strange about this risk is that it has a very specific shape. It is low frequency and high consequence in a way that makes it easy to ignore right up until it is not ignorable. Every year that passes without a truly catastrophic solar event is interpreted by the parts of the system not paying close attention as confirmation that the risk was overstated, when in fact it is simply a year in which the coin came up heads. The Sun does not have a cooling off period after major events. The active region that produced the January 2026 G4 storm rotated around and came back for another pass 2 weeks later. The February X8.1 came from a different region that had been essentially quiet before it exploded into extraordinary activity without much warning. This is the actual operational reality of space weather. Events come from regions that are currently visible and tracked, but also occasionally from regions that seemed unremarkable and then weren't. And the most extreme events are also the hardest to predict far enough in advance for the most complex protective measures to be taken. The 30 to 60-minute window at L1 is genuinely the last line of warning for the most dangerous component of the event, the magnetic field orientation that determines severity. Everything before that is probability estimation. Everything after that is response. Thinking about the Sun from the perspective of deep time produces a kind of vertigo that is different from most other scientific vertigos. The Sun has been doing this for 4.5 billion years. The solar wind has been blowing continuously for 4.5 billion years. CMEs have been detaching from active regions and traveling through the inner solar system for 4.5 billion years. Mars lost its atmosphere to the solar wind after its magnetic field collapsed roughly 4 billion years ago. And the thin carbon dioxide envelope that remains is all that is left after 4 billion years of solar wind stripping. Earth kept its atmosphere because Earth kept its magnetic field, because Earth's iron core has not fully solidified, because the planet is large enough and compositionally right to maintain an internal dynamo. These are not small contingencies. The difference between Earth and Mars, between a planet with a rich biosphere and a planet that is a frozen desert, is partly a question of internal geology that determined whether the magnetic field survived, which determined whether the solar wind stripped the atmosphere, which determined whether liquid water could persist on the surface, which determined whether life could originate and survive. The same star that is currently testing North American power grids is the star that shaped the basic habitability conditions of every planet in this solar system over geological time. The CME that hit Earth in January 2026 was an ordinary event by the Sun's 4.5 billion year operational history. It was a notable event by the 200-year operational history of electromagnetic infrastructure. The gap between those two timescales is where all the interesting problems live. The forecasting skill improvement that the space weather community is working toward over the next decade or two has a specific set of milestones that researchers discuss when they are being concrete rather than aspirational. The first is reliable prediction of CME magnetic field orientation more than 1 hour before arrival. This is the capability that would most directly improve protective actions for grid operators and satellite operators, and it requires either a new spacecraft positioned further sunward than L1 or a significant improvement in coronal magnetic field modeling based on Parker Solar Probe and Solar Orbiter data, or both. The second is reliable prediction of solar energetic particle event onset and peak flux within minutes of flare detection. This is what aviation and astronaut safety require, and it depends on better understanding of the particle acceleration mechanisms in the corona. The third is reliable prediction of which active regions will produce major flares 24 to 72 hours in advance. This is what would allow the most comprehensive protective measures to be pre-staged rather than reactive. Of these three capabilities, the third is the hardest and the most dependent on fundamental advances in understanding the solar dynamo and coronal physics that Parker and Solar Orbiter are beginning to provide. Whether the timeline for achieving these capabilities runs 10 years or 30 years depends on how much resources are directed toward the underlying science and on whether the Sun cooperates by providing enough major events for the models to be validated against. Without those events being severe enough to cause the damage the improved forecasting is meant to prevent. The aurora photography community, the thousands of people around the world with dedicated aurora tracking apps and expensive cameras who travel to high latitudes specifically to photograph the lights, has become an accidental distributed sensor network for space weather events. During the January 2026 storm, the density of aurora photographs posted online within hours of the CME arrival provided real-time qualitative information about the geographic extent and intensity of the event that supplemented the formal instrument readings. Aurora visible from southern France is a different intensity indicator than aurora visible only from Scotland, and the social media photographic record provides a kind of ground truth for the geographic reach of the event that is genuinely useful for post-event analysis. This is not how the field planned to acquire distributed observational data, but it has become a real and useful source. The community that pursues aurora photography for aesthetic reasons is simultaneously, without particularly meaning to, providing scientific documentation of the events they are photographing. The Sun has been doing this for 4.5 billion years. The Accidental Monitoring Network has been operational for perhaps 15 years. Both timeframes are appropriate to the respective participants. The radio astronomy community is another inadvertent space weather monitor. Radio telescopes attempting to observe distant objects, pulsars, quasars, galaxies at cosmological distances, use the ionosphere as a medium that their signals must pass through, and the condition of the ionosphere directly affects the quality of their observations. During major geomagnetic storms, the turbulent ionosphere produces scintillation effects that smear and distort radio astronomical signals, temporarily reducing the sensitivity of ground-based radio telescopes to their targets. The astronomers studying the cosmic microwave background, or searching for gravitational wave counterparts, or monitoring pulsars for timing anomalies, are affected by the same plasma wave that is disrupting aviation communications and bird navigation. The same event leaves its signature in the data archives of radio telescopes as a period of degraded observing conditions, identifiable in the data years later as a gap or a period of elevated noise. The Sun inserts itself into the archives of observatories, studying phenomena billions of light years away, as an interruption, as a reminder that no observation platform on Earth is entirely free of the star it orbits. What would actually change the risk profile, not incrementally but fundamentally, is a combination of three things happening simultaneously. The first is space-based early warning capability that provides reliable magnetic field orientation data hours rather than minutes before CME arrival, giving grid operators enough time to implement the most extensive protective configurations rather than just the fastest ones. The second is widespread installation of blocking capacitors or similar protective devices in high-voltage transmission lines, which is technically straightforward and has been demonstrated to work, but has not been mandated at the scale necessary to protect the full grid. The third is replacement of the oldest and most vulnerable large power transformers with units designed to the most current geomagnetic resilience standards, which is expensive and slow, but not technically impossible. None of these three things requires a scientific breakthrough. They require decisions, regulatory decisions, procurement decisions, budgetary decisions, by institutions that have competing priorities and limited attention. The solar cycle will not wait for the decisions. It is operating on its own schedule, which it has been maintaining for 4.5 billion years, and which has no particular regard for the institutional timelines of the civilization that arrived recently in its neighborhood and built things that it can break. The event that has not yet happened, the one that the ice cores suggest is within the Sun's documented capability, would clarify all of these questions in a way that current events do not. A 10 times Carrington SEP event, accompanied by a direct CME strike with a maximally southward magnetic field, sustained for 12 or more hours, would test every element of the current preparedness framework simultaneously. It would test whether the warning systems provide useful lead time or whether the arrival precedes the forecasts, as the January event did. It would test whether grid operators can implement protective configurations fast enough when the event is developing faster than the models predicted. It would test whether the satellite fleet can survive particle doses that exceed design specifications. It would test whether the communications infrastructure needed to coordinate emergency response remains functional when the ionosphere it depends on is being actively disrupted. And it would test whether the public and political response to a multi-week or multi-month infrastructure disruption, power unavailable, GPS non-functional, many communication satellites damaged, is something that existing social and governmental structures can manage. The answers to all of those questions exist. They are just not known yet, because the event that would reveal them has not occurred within the operational lifetime of modern infrastructure. and every year it does not occur is a year in which the urgency of finding out the answers before the event, rather than during it, recedes slightly from institutional consciousness, until the next major storm restores it briefly before the storm passes and the urgency fades again.